In early 2023, a sudden, almost invisible shockwave hit China's high-speed rail industry. Without any warning, Germany and Japan, two of the world's most advanced exporters of precision rail components, announced they were halting all exports of high-speed rail bearings to China. No negotiations, no grace period, just an immediate, hard stop. To most people, it might have seemed like a minor trade hiccup, but for those who understood the stakes, it was more like a bolt out of the blue, a direct threat to one of the crown jewels of China's infrastructure, its bullet trains. Imagine trying to run a fleet of airplanes, only to discover tomorrow that the engines are gone. That's the level of disruption we're talking about. The global media reacted instantly. Headlines screamed, "China's bullet trains at risk." Analysts warned that without these bearings, the entire system could grind to a halt in months. Hundreds of thousands of passengers, tens of thousands of kilometers of track, and a national symbol of technological pride suddenly hung in the balance. This wasn't just a story about trains, it was a story about leverage, control, and vulnerability, and it set the stage for a dramatic question. Could China keep its high-speed rail network running when a tiny, seemingly simple component had been suddenly cut off? This wasn't a random trade spat or a simple business decision. What Germany and Japan did was a textbook example of technological containment, a way to exert control by restricting access to the critical components that keep a system running. Bearings might seem small, almost insignificant to an outsider, but in reality, they were the linchpins of China's high-speed rail network. Without them, trains can't move safely or efficiently. And because these trains are not just transportation, they're symbols of national pride and technological progress, the stakes were as much political and strategic as they were industrial. In other words, a tiny ring of steel suddenly became a national vulnerability. One missing part, and the entire network could face delays, failures, or worse. It was a reminder that in high-tech systems, control over even the smallest components can mean control over the entire machine, and, by extension, influence over a nation's ambitions. This wasn't about money, it was about leverage, power, and sending a message. You may have built this network, but you don't fully control the technology. And for China, that message hit hard, setting the stage for a challenge that would push the country to innovate under pressure. To grasp the gravity of this situation, you have to understand the sheer scale of China's high-speed rail network. This isn't just a collection of trains running on tracks. It's the largest and most ambitious system of its kind on the planet. Tens of thousands of kilometers of steel weave across mountains, plains, and deserts, connecting far-flung provinces at speeds that can exceed 350 kilometers per hour. That's faster than most commercial airplanes during takeoff. Every element of this network has to operate in perfect harmony. From the sleek, fuxing bullet trains to the intricate signaling systems, every component must meet microscopic tolerances. One small flaw, and the consequences can ripple across the entire system: delays, mechanical failures, or in the worst case, accidents. And that's where the danger of the export halt becomes crystal clear: the bearing. It's a component so small it can fit in your hand, yet it sits at the heart of wheels, motors, and gear assemblies, ensuring everything rotates smoothly. Without it, the trains would grind to a halt, literally. Imagine constructing a massive suspension bridge and realizing that the tiny bolts holding the main cables together were suddenly gone. The structure itself would be at risk. That's the scale of this problem. China had spent over 2 decades building this network, turning high-speed rail into a symbol of national pride, engineering ambition, and global prestige. Yet in an instant, the entire system's reliability hinged on a single, seemingly modest component. The stakes couldn't have been higher. This wasn't just an engineering challenge, it was a national crisis disguised in miniature. And this tiny but critical vulnerability set the stage for a larger story, a tale of dependence, innovation, and the relentless drive to turn a potential disaster into an unprecedented technological triumph. So, what exactly makes a bearing so important? To put it simply, bearings are the joints of a machine, just like the joints in your body. They allow movement to happen smoothly, absorb stress, and keep everything aligned under pressure. In a high-speed train, bearings are tucked inside wheels, motors, and gear systems, quietly doing the work that makes 350 kilometers per hour speeds possible. But don't let their size fool you. A single bearing in a high-speed train must endure tremendous forces, heat, vibration, and wear every second it spins. If one fails, it can trigger a chain reaction derailments, system-wide delays, or catastrophic mechanical failures. The tiny rings of steel carry the enormous weight of entire trains, rolling thousands of kilometers under extreme conditions. Think of it like a human knee in a marathon. Your knee supports hundreds of pounds of motion over long distances, and if it fails, your whole run stops. Or worse, you get seriously injured. Bearings are the same for trains, small but absolutely essential, invisible heroes that hold the system together. Despite China's rapid progress in building trains, tracks, and software, bearings remained a vulnerability. Producing them isn't just about shaping steel. It's about ultra-precision engineering, microscopic accuracy, and decades of know-how. One tiny imperfection can make an entire train unsafe at high speeds. This is why the sudden export halt wasn't just an inconvenience. It was like someone had pulled out the keystone in an arch. A small part, yes, but one that could bring a massive system to a grinding halt. And that's exactly what made this story so high stakes and dramatic. At first glance, it might seem surprising. China builds skyscrapers in weeks, launches rockets with precision, and dominates global manufacturing. So why couldn't it just make its own high-speed rail bearings? The answer lies in the extreme demands of the task. High-speed rail bearings aren't ordinary steel rings. They require exceptional metallurgy, microscopic precision, and decades of specialized expertise. The slightest flaw, an air bubble, a microscopic crack, or uneven metal grain, can cause catastrophic failure at 350 kilometers per hour. You can't simply order a machine, twist a dial, and have world-class bearings emerge. For decades, Germany and Japan held a near monopoly on this technology. Companies like Schaeffler and NSK controlled not just the bearings, but the entire supply chain, from raw materials to ultra-pure steel and precision finishing. They had refined their processes over generations, building expertise that isn't easily copied. This created a stark contrast. China could dominate large-scale industrial projects, but this one tiny component revealed a critical vulnerability. It exposed a gap where foreign control could literally stop the trains. One small piece of steel became a symbol of dependence, proving that even the most advanced infrastructure can hinge on a single point of weakness. The challenge was clear. If China wanted independence, it couldn't just catch up. It had to master one of the toughest industrial sciences in the world. And that journey was about to begin. The heart of the problem wasn't just shape or size. It was the steel itself. High-speed rail bearings require a type of metal known as bearing steel, and it's not your average construction steel. This steel has to be ultra-pure, perfectly uniform, and incredibly strong, capable of withstanding extreme heat, pressure, and vibration without even the tiniest flaw. To put it in perspective, the steel must have less than 5 parts per million of oxygen. Imagine trying to remove every speck of dust from an Olympic-sized swimming pool. That's the level of precision needed. Even a microscopic impurity can create gas bubbles or weak spots, turning a bearing into a potential disaster waiting to happen. Producing this steel is a nightmare of complexity. It requires vacuum smelting, precise alloy mixing, and controlled cooling down to fractions of a degree, repeated perfectly across massive batches. One small mistake, and the whole batch becomes unusable. This is why Germany and Japan had the upper hand. Their companies had spent decades perfecting every step of this process. They didn't just sell bearings, they controlled the knowledge, the secrets, and the precision. For China, it wasn't just about building a bearing, it was about unlocking the entire science behind the steel itself. In short, the challenge wasn't small. It was a test of industrial mastery, material science, and relentless precision. And it was this challenge that would push Chinese engineers to rethink what was possible. The sudden halt of bearing exports from Germany and Japan wasn't just a supply problem, it was a wake-up call. For years, China had relied on foreign expertise to fill the gaps in its high-speed rail program. Bearings were a quiet bottleneck, a weak link that the rest of the world quietly controlled. Now that dependence was laid bare. Foreign experts didn't hide their skepticism. Some openly mocked China's efforts to catch up, labeling the country as a low-end manufacturer, good for mass production but incapable of mastering precision engineering. The message was clear. You might build trains, but you'll never match our bearings. Yet this critique had the unintended effect of lighting a fire under Chinese engineers. Instead of accepting defeat, they saw the blockade as a challenge, an opportunity to prove that China could not only catch up, but surpass the very countries trying to contain it. The stakes were enormous. This wasn't just a supply chain hiccup. It was a strategic message. The world was saying, we control this technology. Without us, you are vulnerable. For China, the choice was stark. Remain dependent and risk collapse, or innovate and reclaim control. This moment transformed a crisis into a catalyst for innovation. It forced the country to examine its entire industrial ecosystem, from metallurgy to machining, and ask a single question. How can we build bearings that meet the highest global standards entirely on our own? What had started as a threat to national infrastructure now became the spark for a quiet revolution, one that would redefine China's place in global high-tech manufacturing. While headlines focused on the speed of China's bullet trains or the expansion of its network, far from the spotlight, a quieter, more profound effort was underway. In the central province of Henan lies Luoyang, an ancient city better known for its history than for cutting-edge industry. Yet here, at the LIC Bearing Corporation, a small team of engineers was quietly taking on one of the world's toughest industrial challenges. These engineers weren't designing flashy trains or futuristic stations. They were obsessed with microns, steel chemistry, and durability curves. Every day they analyzed the tiniest imperfections, ran endless simulations, and tested materials under extreme stress. Their mission, to close the gap between Chinese bearings and the world's best. What made Luoyang remarkable wasn't just technical skill, it was persistence. While the rest of the country celebrated high-speed rail milestones, this team worked in near silence, driven by a single goal: self-reliance and mastery over a critical technology. They treated every setback as a lesson, every tiny improvement as a step toward global competitiveness. In many ways, Luoyang became the heart of China's response to the blockade, a place where ingenuity, discipline, and determination transformed what could have been a crippling weakness into a laboratory for innovation. The revolution wasn't noisy or dramatic at first. It was quiet, relentless, and precise, just like the bearings these engineers were determined to perfect. After years of meticulous research, testing, and iteration, the engineers in Luoyang achieved what many had thought impossible. Against the backdrop of the 2023 export blockade, LIC unveiled a fully domestically produced high-speed rail bearing, certified to operate reliably at speeds of 350 kilometers per hour on China's flagship Fuxing bullet trains. These bearings didn't just meet standards, they were put through brutal, real-world simulations. Over 1 million kilometers of testing mimicked the stresses of heat, vibration, pressure, and speed, pushing the bearings to their limits. And they didn't just survive. In some key metrics such as heat resistance, wear durability, and dimensional precision, the Chinese bearings outperformed their German and Japanese counterparts. A major breakthrough came from rare earth microalloying, a technique where minute amounts of rare earth elements are added to the steel during smelting. This strengthened the grain structure, increased fatigue resistance, and improved overall performance. Ironically, this method had long been a closely guarded secret of foreign firms, until Chinese engineers discovered their own version. In a dramatic reversal, the same component that had once symbolized dependence now became a symbol of innovation and self-reliance. The tiny bearing, once a potential choke point, had been transformed into a triumph of engineering, strategy, and national determination. This was more than a technical win. It was the moment the story turned from crisis to capability, from limitation to leadership. China had not just survived a blockade, it had redefined the rules of the game. The breakthrough in bearing production wasn't just a technical victory, it had real-world consequences for China's economy, industry, and global standing. Let's start with the numbers. Each domestically produced high-speed rail bearing saves roughly $32,000, or about $4,400 per rail car. That may not sound like much until you consider that China operates tens of thousands of high-speed rail cars across its vast network. Multiply that across the fleet, and the savings add up to hundreds of millions of dollars, money that can now be reinvested into expanding the rail system or developing new technologies. But the impact goes beyond economics. Strategically, China eliminated a critical vulnerability. Bearings had been a choke point where foreign control could halt trains and exert pressure. By mastering this technology, China turned a weak link into a strength, ensuring that no single foreign supplier could threaten its national infrastructure again. There was also a symbolic victory. For years, foreign experts had dismissed China as a nation of assembly lines, good for low-end production but incapable of mastering high-precision engineering. The 2023 blockade was meant to reinforce that narrative. Instead, it became a story of resilience. China transformed dependence into innovation, imitation into leadership. In short, the bearings were no longer just components. They were symbols of economic efficiency, strategic independence, and national pride. What had started as a crisis now marked a turning point in China's industrial and technological journey. Achieving a breakthrough bearing once was a monumental win, but doing it reliably at scale across thousands of trains was an entirely different challenge. China quickly realized that innovation wasn't just about steel and precision. It required people, machines, and a complete industrial ecosystem working in harmony. First, talent. Back in the 1980s and 90s, Chinese universities offered specialized programs in bearing design and manufacturing, producing engineers with rare expertise in precision motion. Over time, these programs were phased out because demand for high-end bearings seemed low. Now, the country faced a shortage of skilled engineers who could handle the extreme tolerances and advanced techniques that modern high-speed rail bearings demand. To fill the gap, companies like LIC and the government invested heavily in training centers, vocational schools, and university partnerships, reviving a generation of bearing experts. Next, the machines. Producing bearings to nanometer-level tolerances requires state-of-the-art CNC equipment, ultra-sensitive measurement tools, and automated quality control systems. Even a human hair is 75,000 nanometers wide, yet a bearing's margin of error can be less than 100 nanometers. Scaling production meant upgrading machines, software, and sensors to meet these extreme standards. Finally, the ecosystem. Bearings rely on ultra-pure steel, advanced lubricants, testing platforms, and simulation software. To remain independent, China had to strengthen every link in the chain, from refining steel purity to developing the automated systems that ensure consistent quality. In short, producing a breakthrough bearing was just the beginning. To sustain leadership, China needed a holistic approach, combining talent, technology, and industrial infrastructure, transforming a single victory into a lasting advantage. China's success with bearings didn't stay a domestic story for long. It began to reshape perceptions around the world. What was once seen as a minor, overlooked component suddenly became a marker of industrial prowess and technological independence. Chinese bearings started entering global supply chains in sectors like automotive, industrial machinery, and even rail systems outside China. In a striking twist, some foreign companies were caught relabeling Chinese bearings and selling them under their own brands in Europe. This wasn't just an ethical issue, it was an admission. These products were now competitive at the highest level, even against the companies that had once tried to block China's access to the technology. The story is a powerful illustration of transformation. China moved from being a dependent player, importing precision components from abroad, to an influencer in the global high-precision manufacturing arena. Competitors who once dismissed China as a producer of low-end goods now had to reckon with its capabilities. In other words, the same bearing that had symbolized vulnerability and dependence had become a symbol of strength, innovation, and global respect. It proved that technological self-reliance isn't just about survival. It can also reshape markets, challenge norms, and rewrite the rules of competition. China's journey with bearings is more than a story about steel and machines. It's a lesson in how persistence, strategy, and innovation can turn a crisis into global influence. The story of China's high-speed rail bearings is more than an engineering tale. It's a lesson in resilience, strategy, and the power of innovation under pressure. A small, palm-sized component, once a point of vulnerability, became the spark that transformed a national crisis into a symbol of technological self-reliance. The key takeaway is clear core technologies can't simply be bought. They must be built. From bearings to semiconductors, aerospace, or biotech, dependence on others can create fragility. But when a nation decides to innovate and master its own capabilities, a vulnerability can become a launchpad for global leadership. China's journey also reminds us to look beyond the obvious. It wasn't the trains, the tracks, or the stations that defined success. It was the quiet work of engineers behind the scenes, obsessing over microns, chemistry, and precision. Innovation often happens in places the spotlight never reaches. So, next time someone tells you a small part doesn't matter, remember the bearing. It's proof that even the tiniest elements can shape the fate of nations. If you found this story inspiring or eye-opening, make sure to like, share, and subscribe. Stay curious, because the world is full of hidden engineering marvels and the people who refuse to let obstacles define them.